Hello, I'm glad to present our work on vanishing point aided hash frequency encoding for neural radiance fields from sparse 360-degree input.
Neural Radiance Fields and its successors have been groundbreaking in the field of biosynthesis. When combined with omnidirectional images, they simplify the creation of photorealistic 360-degree environments for VR and AR applications. NeRF represents a scene as a continuous function that maps the coordinates x, y, z and viewing direction theta phi to the color RGB and opacity sigma of sampled 3D points. Given a set of input images, the weight of a NeRF model is optimized by minimizing the photometric loss. A well-trained NeRF model can synthesize novel views with remarkable fidelity.
Why is NeRF so successful?
A key component of NeRF is input encoding, which lifts the input coordinates to higher dimensional frequency features. Usually, it is calculated using a series of sinusoidal functions with varying frequencies. This technique allows the neural network to effectively capture the fine details within the scene.
Many powerful and efficient encoding methods have been developed.
The multi-resolution hash encoding proposed in Instant NGP represents a significant advancement in NeRF. It dramatically enhanced the previously slow optimization and inference speed. This method employs multi-resolution grids with corresponding hash tables to enable a learnable and localized feature mapping for input coordinates. Thanks to hash encoding, the NeRF now can be optimized within minutes.
However, despite its rapid convergence, we have observed that this method can fail easily when the input views are sparse and distant. This can lead to catastrophic failures in reconstructing the scene. For instance, in a 360-degree scene sampled with only 8 panoramas, each more than 1 meter apart from the adjacent view, artifacts such as ghosting, floating objects, and incorrect geometry become visible everywhere. Moreover, previous research has revealed that positional encoding tends to show a bias towards signals with more frequency content along the axis. So when we align the x, y, and z axes with the scene structure, we observe a notable improvement in quality of NeRF's reconstructions. Our motivation here is to improve the NeRF with sparse 360-degree inputs and refine the reconstruction of scene structure for indoor and city scenes. To address these challenges, we leverage the spatial smoothness and consistency offered by frequency encoding. We explicitly align the scene structure with the frequency encoding by estimating vanishing point from planar or 360-degree images. The first part of our method involves scene alignment. To achieve this, we extract the scene geometry by estimating the vanishing point from both 2D perspective images and 360-degree images. We employ a convolutional network-based model, Neural VPS, which aggregates the feature along the structural line that converge at the vanishing point. Additionally, we adapt the model for 360-degree images by considering the parallel lines in equirectangular projection. With the knowledge of 3 estimated orthogonal vanishing point directions, we apply a simple rotation to the camera coordinates, ensuring that a significant portion of the scene structure aligns with the axis. Finally, we combine the hash encoding with axis-aligned frequency encoding through a concatenation. We found that this combination improved the robustness of hash-based NeRF when dealing with limited input views, particularly in scenarios with imperfect scene scaling. Our model builds upon the foundation of a recent hash encoding-based pipeline called NeRFactal. For scenes with limited input, our method demonstrates a remarkable improvement over NeRFactal while maintaining the efficiency of hash encoding. Due to the nature of vanishing points, we acknowledge that the scene alignment can be less effective in natural scenes or scenes with non-orthogonal vanishing points. Our next step is to explore solutions that enable local alignment of texture and geometry in such challenging scenarios. Additionally, the selection of optimal frequency band can be a complex and empirical task. Determining the most suitable frequency band relies on the specific input setup and scene content. Thus, our future work aims to develop methods for more robust and context-aware frequency band selection. Thank you all for your attention. If you are interested in our work, we encourage you to explore our original paper and supplementary materials. We also welcome any questions and further discussions, so please feel free to reach out to us.